Statistics Week 8, Part 6. A single population mean using the student t-distribution. In practice, we rarely know the population standard deviation. When the sample size is large, this doesn't represent a problem to statisticians. They use the sample standard deviation S as an estimate for sigma and proceed as before to calculate a confidence interval with close enough results. However, a small sample size causes inaccuracies in this confidence interval. With graphing calculators and computers, the practice now is to use the student's t-distribution whenever S is used as an estimate for sigma, instead of the normal distribution. If you draw a simple random sample of size n from a population that has an approximately normal distribution with mean mu and unknown population standard deviation sigma, then you can calculate the t-score, which is like the z-score but is given by this formula. T equals x bar minus mu over s divided by the square root of n. Now that's very similar to the z-score formula that we used in Chapter 7, modified for the central limit theorem, but you'll notice that here, instead of sigma, we have an s for the sample standard deviation. With this, then the t-scores follow a student's t-distribution with n-1 degrees of freedom. The degrees of freedom, n-1, just come from the calculation of the sample standard deviation s. So essentially, n-1 is just the sample size minus 1. The t-score has the same interpretation as the z-score. It measures how far x bar is from the population mean mu. For each sample size n, there is a different standard student's t-distribution. The student's t-distribution, as we'll see, looks very similar to the normal distribution, and it behaves the same way. The properties of the student's t-distribution are these. The graph of the student's t-distribution is similar to the standard normal curve. The mean of the student's t-distribution is 0, like our standard normal distribution, and the distribution is symmetric about 0, like the normal distribution. In fact, if you look at this graph, you'll notice that the dark red line represents the normal distribution, and the other colored lines represent the student's t-distribution for 1, 2, 5, and 20 degrees of freedom. All of them look very similar, but the tails contain more area. That won't really concern us because we're really interested in the symmetry and the fact that we can do our calculations the same as we did for the normal distribution. Using the student's t-distribution. The notation for the student's t-distribution using t as a random variable is this. T is a random variable represented by t sub df, where df is equal to n-1. df stands for degrees of freedom. An example would be if we have a sample size n equals 20 items, then we calculate the degrees of freedom as df equals n-1, which is 20 minus 1, or 19, and we write the distribution as t is the random variable represented by t sub 19. The error bound for the mean is given by t sub alpha over 2, so you'll see that's almost the same thing as our z-score, except we will have to calculate it differently, and we have s divided by the square root of n, where s replaces sigma, since we do not know the standard deviation of the population. The t-score, like in our previous examples, represents the area to the right equal to alpha over 2, and s is the sample standard deviation. The format for the confidence interval is the same as we did with the normal distribution, x bar minus EBM, comma, x bar plus EBM. Here's an example. Suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure the sensory rates of 15 subjects with the results given. We're going to use the sample data to construct a 95% confidence interval for the mean sensory rate for the population, which is assumed to be normal, from which we took the data, represented here. Now, this data you would simply plug into your calculator or a spreadsheet, and then use the statistics function to get the sample standard deviation and the sample mean. However, you'll notice in this paragraph there's no mention of a population standard deviation or mean. So, we first need to find the sample mean and then the EBM. The sample mean turns out to be 8.2267 the sample standard deviation 1.6722, and of course our sample size is 15. So we'll go about calculations in a similar way, but we will add finding df, so degrees of freedom, which is 15 minus 1 equals 14. Our confidence level is 95%, so that calculation is identical to what we did before, getting an alpha over 2 of 0.025. The area to the right of T alpha over 2 is T 0.025. So again, like we did with the normal distribution, area to the left is 1 minus 0.025 or 0.975. Now, if you have a TI-84 calculator, you'll be able to use this directly to calculate using the inverse T function. If you do not have a TI-84 calculator, this is not a function that's on the TI-83, and you'll either have to use an internet resource or look the values up in a T-table, which has actually been included in this week's materials. Use the inverse T calculator function or table to find that T alpha over 2, T 0.025, is 2.14. So our error bound for the mean is T alpha over 2 times S over the square root of n, which is 2.14 multiplied by 1.6722 over the square root of 15, or 0.924, rounded to 3 digits. That gives us our error bound mean, and finally our confidence interval will be, after short calculations, 7.30 to 9.15. Here's a try-it exercise for you to apply what you've just learned. Pause the video and then check the results after you've done your calculation. Here are the results. X bar is 8.9833, S is 1.2904, and N equals 12 for our sample. There are 11 degrees of freedom, and our confidence level is 95%, so alpha over 2 is 0.025. The area to the right of T sub alpha over 2, or T equals 0.025. So the area to the left is 1 minus 0.025 equals 0.975. You can use the inverse T function on the TI-84 calculator to find that the result is 2.20. If you do not have a TI-84 calculator and you need to use the T-table that I've included in the materials for this week, then you'll need to use the value for the right, 0.025, and you'll see that as a column header on the table, and then the degrees of freedom down the left-hand side. The error bound for the mean is going to be 0.8195, and then your confidence interval by using the mean will be 8.16 to 9.80. Here's another example using the student's T-distribution. Scientists at the Human Toxome Project tested cord blood samples for 20 newborn infants in the United States. The cord blood of the in utero newborn group was tested for 430 industrial compounds, pollutants, and other chemicals. There are health concerns about the effects of some chemicals on the brain and the nervous system. Use this sample data to construct a 90% confidence interval for the mean number of targeted industrial chemicals to be found in an infant's blood. Here's the data set, and if we compute the mean and the standard deviation for that, we'll find that X bar is 127.45, S is 25.965, and there are 20 infants in the sample, so N is 20. There are 19 degrees of freedom. You're asked to calculate a 90% confidence interval, so CL is 0.90, and T of alpha over 2 is T 0.05. By definition, the area of the right, 2.0.05, is 0.05, so the area on the left is 0.95. We use the calculator to compute that our T value is 1.729 for 19 degrees of freedom. Our error bound is 10.038, and that gives us a confidence interval of 117.412 to 137.488. We estimate with 90% confidence that the mean number of all targeted industrial chemicals found in cord blood in the United States is between 117.412 and 137.488.